Hi, everybody. Welcome to our final round, at least for now, of Fellows Talks. Today we have Andrii, Layan, Refilwe, and Sam. So up first is Andrii. Andrii, whenever you want to get started, go right ahead.
Yeah, thank you. I was a fellow this summer, and together with my mentors Enrico and Alex, we worked on implementation of Analysis Grand Challenge with RDataFrame. Let me first explain what is Analysis Grand Challenge. As you probably know, the Analysis Grand Challenge is all about developing and testing data analysis workflows and version for the high-luminosity LHC with a goal to firstly be equipped for future runs, and secondly to demonstrate performance of our software tools which are being developed by IRIS-HEP community and partners. And the Analysis Grand Challenge basically has two major pieces. The first is specification of analysis task, and the second is reference implementation. We have IRIS-HEP reference implementation, and the goal of our project was to do the same results with RDataFrame. Why RDataFrame? RDataFrame is entry point to Root's modern analysis interface. It allows flexibly express many things in HEP analysis. It gives us seamless scaling out to computing clusters, and the goals for this summer were basically to move our RDataFrame implementation to a newest version of Analysis Grand Challenge. Few words about specification. The analysis task is measurement of cross section of producing top quarks, and to accomplish this task, we need to solve two problems. The first is event selection. We need to, in some way, we have some algorithm to distinguish background events from signal events from background events. And the second is how to calculate the observable, because here is not only one way to do that. Some algorithms could be more efficient, some can be less efficient. Another important thing here is that after calculating observable, we also need to do statistical inference, but we left it for future project. In this project, we were focusing on event selection and on calculation of observable. To select events, we used semi-electronic decay schema. In this decay channel, we expect to see two jets, two beta jets, and one lepton. And observable we are deriving here is reconstructed top mass. And let's go into some details. We already had RDataFrame implementation with version 0. And in this slide, you can see different selection cuts applied to select those events we need. And what we have done, we switched it to new data schema. We added new selection cuts, which are more complicated in our implementation. And we added boosted decision trees to perform inference, which is used to jet pattern assignment. This is like some summary, and here, and here I will provide a bit more details. This is slide about how we derive our observable. In the semi-leptonic decay schema, judging from this diagram, we can see that to find mass of top quark, we could just to use masses of 3 jets, anti-B, some anti-quark, and quark. They are not defined. And to do that, we first need to select events with at least 4 jets, because otherwise it can't be the decay product of top quark. And now the question is, how can we choose the best combination of 3 jets, which is the product of top decay? There are 2 ways. No, much more, but we do that in 2 ways. The first is without, it is simple way without applying machine learning. It's old way to do so, as was in previous implementations. Firstly, we built all 3-jet combinations and assign to each combination some properties, some features from which we are concluded and infer the best candidate to be the decayed product of top quark. The first property is there at least one big target jet? If yes, it's okay. And the second is total transverse momentum. It's just summing up of all transverse momentum of each jet in combination. And then we need to set some criteria how to decide from these properties is any particular which permutation or combination from all these are the more probable. In our case, we just choose combination with highest transverse momentum. These histograms are produced with algorithm explained above, and this is a comparison between our implementation and coffee. This is not all the histograms, just a particular example. And to summarize it, all of our 122 histograms are in perfect alignment, bin by bin. But it's worthy to mention that we observed some bin migrations. You can ask me a question about it if you are interested, but I will move on. The second part was machine learning. Why it is needed? As you remember, in a previous slide, we used very not very reliable criteria. We just chose combination with highest transverse momentum. The question is why? Why so? Each trijet combination has lots of information, but we asking only about transverse momentums. So to solve it, we basically use machine learning. Why? Because it allows us create more complicated logic to choose the best candidate. We can construct much more features, or it is just properties for jet combinations to express more physics. And the key point here is that we can delegate the work of making decisions for creating criteria how to decide to computer. Few words about how it works. It works via boosted decision trees. The decision tree express some logic. Every node, every rectangle is node represents some decision, and that decision makes in recursive way each node is just a split which decide is any particular combination pass some threshold or not. And sorry, I was muted. In output, we have only those combinations which are past the thresholds and they are probable candidates. Why it works? Because we can create a forest of decision trees. There are many of them. And we, in machine learning, we delegate to the computer the draw the content of each each tree by fitting the model with data. If you're familiar with machine learning, I am speaking just about training. So we do not apply some artificial, not very natural criteria to choose best combination. We delegate this work to computer, and it derives those criteria from training data. This is much more efficient. And this slide shows the actual implementation. Imagine the event we have in which we have 4 jets, and what we do, we build all possible combinations of 4 jets by assigning 3 labels to 4 jets. I mean, not all possible, but all unique permutations. It's important. And for each permutation, we calculate 20 features, not 2 as was in previous implementation, but 20. And we feed those features to a pre-trained model. And those this pre-trained model perform inference and gives probability for each candidate to be the product of decay of top quark. See full details in official documentation. And these histograms are showing again the comparison between our implementation and coffee. And important note that only 9 out of total 100 20, only 9 of them are within small tolerance, 1%, but all other are perfectly matched bit by bin. And this is our performance benchmarks. So the key points here is that we observe significant speed up, not perfect, because perfect would be from 1 core to 64. We expect speed up 64, but in our case it is 41, but it is enough good. Some problem we can observe with memory, but we need to still to investigate what's going here, why memory is not growing linearly. Yeah, let me summarize all what we have done. We switched our implementation to version 1, which is switching to new input data schema nano out. Then we switched our implementation to version 2. In particular, we defined new selection cuts, added calculation of features, added inference, and it was very complicated task because we also integrated our implementation with another C++ library called Fast Forest. And in our Python implementation, we actually have behind that 2 libraries, root and Fast Forest, and integrated all this together. And we have good validation in terms of alignment with reference implementation and performance benchmarks. Thank you for your attention. If any questions, I will answer with yeah, I will answer.
Thank you, Andrii. Any questions for Andrii? Alex or Enrico, you want to add anything to?
Yes, of course. So as you saw, this was a project with lots of moving parts, right? There is the mixing of C++ and Python with just-in-time compile C++. There's the physics background of all of this, the machine learning component. And when all of this was done, you look at the final histograms, and some bins of some histograms have some discrepancy, with reference implementation, and you have to go in and figure out if it's just floating point errors or something more serious. So it took some serious commitment and skills to push through all of this, and we're very happy with the result. So thank you very much, Andrii, for all your hard work.
Great. Some applause from Alex. So
yeah, I have nothing to add. Beyond that, thanks a lot. Super nice to see all of this work happen and all of the outcomes here presented.
Yeah, thank you. I'm very thankful to my mentors and to all organizers too.
All right, thank you, Andrii. Up next is Layan.
Hello everyone, my name is Layan, and I'm currently working at Tompkins Lab with Professor Lauren Tompkins. My project this summer was studying a new primary vertex identification algorithm within the ACTS framework. Let's first talk about what are primary vertices. A vertex is the actual proton-proton interaction point in space. And so a primary vertex is the accurate estimation of the inelastic interaction point. In run 3 of the LHC experiment, there were 50 to 70 collisions per event, but we expect that number to become much higher in the next run, about 150 to 200. And therefore, a fast and efficient algorithm is needed as the increase of energies and luminosities in experiments in the future is higher. This is an actual environment, collision environment for ATLAS data. So let's talk about tracks and track reconstructions. Tracks are the paths taken by charged particles while traversing through the detector. But track reconstruction is finding the set of measurements coming from one charged particle and building the associated trajectories. This is a scheme of the point of closest approach to the z-axis for a trajectory. The trajectory is the line in orange, with a particle p with momentum p. Here, the d0 and z0 are the transverse and longitudinal impact parameters. And these are the impact parameters that we're interested in our study, as well as the associated uncertainties for them in order to reconstruct the tracks. A previous primary vertex identification algorithm was built first developed for LHCb, and then later it was adapted for ATLAS. So if you look at the graph on the left, we're comparing the efficiency between the PV finder built for ATLAS data compared to the AMVF, which is the adaptive multi-vertex finder. Excuse me, just a second. Yeah, sorry about the noise outside. Yeah, so the AMVF is the global approach to vertex finding and fitting. And here we're comparing the efficiency between it and Atlas data. And you can see, if you look at the blue and the red, that they have same, if not better, efficiency. As for the graph on the right, we are measuring how good an algorithm functions if there are two close vertices to the z-axis and still be reconstructed as two distinct vertices. So our PV finder in blue is able to distinguish that and reconstruct them as two vertices, but the AMVF reconstruct them as one primary vertex. The approach that we're taking is a deep learning based approach. We start by preparing the input, gathering the input. It consists of track parameters and their uncertainties, as well as truth vertices. We use that input to calculate KDEs, which we will be talking about shortly. So yeah, we transform the tracks and their associated uncertainties into one-dimensional KDE histogram. We feed these KDEs into a DNN-based algorithm, deep neural network-based algorithm, and we expect the output of the predicted primary vertices. In this project, I'm focusing on the first two steps. And by reconstructing the tracks, we can calculate the KDEs, and that's actually sufficient to feed it to a neural network to estimate the primary vertices locations. And so our goal is to train a neural network by giving the machine a set of simulated data in which the primary vertices locations are provided. The network is trained to receive data from the detector's sensors about the position of hits as inputs and give the positions of primary vertices as output. So I've been mentioning KDEs multiple times. What are KDEs? KDE stands for kernel density estimation. It's a probability distribution technique. It transforms the tracks and their measured resolutions into representations of the track density. So a track density of, say, track I at any point in space in the D0 Z0 plane is given by the transverse and the longitudinal correlated Gaussian probability distribution and centered around the D0I, Z0I. This formula is how we calculate the probability density. And the shape of the density distribution is determined by the covariance matrix, sigma I in this case. And if we sum up all the probability density functions at any z point, we can find the global maximum, and that represents the position of highest track density, which is the prediction of the vertex position. So we are using ACTS, which is, or we are implementing this algorithm within ACTS because ACTS is an independent open source framework for track reconstruction in particle physics experiments. What's really special about it is that it works on a generalized algorithms to guarantee that any experiment can utilize it. It provides many essential components such as track models, fitting algorithms, and so on. If you're interested to read more about it, this article could be helpful. Our setup, we are using the open data detector. This is a schematic of the inside of the open data detector. And if you want to read more details about the open data detector, this article has many information. We are generating events using Pythia 8 with TT-bar. And as reference primary vertices, we are generating them through the AMVF algorithm. The events, we have 3,000 events and a pileup of 50, so expect about 300 tracks per event. So as for the algorithm that we've implemented in order to calculate the probability density functions, and hence we're able to generate the KDE histograms, we started by gathering track parameters and their covariances, their uncertainties, generated by CKF algorithm. As I said, we're focusing on D0, Z0. And then we feed these parameters to the KDE generator, the algorithm we've written. And as most ACTS algorithm, it consists of three main components: a constructor, an execute function, and a finalize function. In the constructor, we initialize all the input root files, input trees, input branches, the vectors, as well as the output root files, and so on. In the execute function, we iterate through each event. We sort the tracks based on certain criteria. We defined multiple lambda functions for binning and for the evaluation of the probability density functions. We filter the tracks to only have the desired or good tracks. We calculate the covariance matrix for each track, perform a grid search, and we output the best kernel value for that bin. In the finalize, we just do a cleanup to ensure there are no memory leaks, and we write this data into an output root file. The last step is to run this algorithm on 3,000 events in order to generate a one-dimensional bend histogram with 12,000 bends and a Z range between -24 to 24 centimeters. So we expect the width of bends to be 40 micrometers. This is a snippet of the code. Please do not be intimidated. If you look at the snippet, the upper one, this is where we define the Gaussian probability density function. And it returns, if you remember a few slides ago, the probability density function. It's encoded here. As for the lower snippet, this is just a look into our execute function, where we are calling for the get Gaussian PDF in order to calculate each PDF for each track. If you would like to look at a I'm sorry, there's an emergency earthquake. Yeah, if you would like to take a look at the code, you can find it here. I'm really sorry, but we're getting an emergency earthquake alert. I have to go. I'll try to join later on.
Oh, Layan.
No,
That's just a that's
don't worry about it.
yeah, it's not a real one. It's just a
okay.
like a California-wide drill or something.
Okay.
Yeah, I know. I just did the exact same thing.
Yeah, they didn't warn us. I didn't know.
I only knew because of my kid. But anyways, yeah.
Okay, thank you. All right. So these are the results from our analytical approach, where we hard-coded the function. The KD. So each graph represents, or you can see two KDEs, KDE A and KDE B. KDE A returns the kernel returns the PDF for each track, and KDE B is the square of that. Yeah, so these are our results. Now we want to feed these KDE distributions into a deep neural network to get PV primary vertices predictions. In these graphs, only a small range is shown just to observe the structure. The architecture we're using for so this analytical approach is a slower approach. We need a faster method, and that's where our model for neural network approach for KDEs. So we feed track parameters and their uncertainties, as well as the analytically calculated KDEs, into a fully connected neural network trained on 3,000 events. And then we have KDE predictions. This is a much faster and efficient way. This plot up shows our loss function. And so we trained the model on 3,000 events, and the loss function converged well, as can be seen from the decreasing training and validation loss. This gives us an indication that our model is trained well, and a boost to continue the work. These are the results from our neural network-based approach. In blue, you can see the analytically calculated KDEA, and in pink, the neural network predicted. And there's a good agreement between the two. This approach, or the work on this approach, was done by my colleague Ananya, who is an HSF Indian fellow. If you have questions, you can send her an email for any details about this approach. So as a conclusion, we completed the first step in the project. As a reminder, our project is to build a deep learning-based primary vertex identification algorithm within ACTS. We have compared the results from our analytical approach and our neural network approach. A drawback in our analytical method is that producing these KDEs takes a really large runtime. And so our next step is to feed KDEs into the DNN to get PV predictions, and to use neural network for KDE generation in order to save the time. Ananya is already working on it. It's good to point that we're integrating this algorithm within ACTS to enable other experiments to adopt it for broader use. Thank you, everyone, for your time.
Well, thank you, Layan. Any questions for Layan? Lauren, do you have anything you'd like to add to?
No, it's just been a real pleasure working with her. Yeah, we're looking forward to actually having this available in ACTS.
Great. Thank you. There you go.
Okay, hi. My name is Refilwe, and for my project, I was working on novel edge classification architectures for charged particle tracking with graph neural networks, and I was working with Dr. Killian Lurid and Gage Dazut. So what is tracking? So we essentially use tracking to track the positions, velocities, and trajectories of particles over time. And the data is normally represented as graphs where particle hits are nodes and their trajectories are represented as edges. So if you have two nodes and one edge, one particle trajectory from one node to one node, then that would be the edge. And track reconstruction is essentially connecting the dots between multiple nodes. So again, for node representation, those are particle hits, and to propagate information between connected nodes, we represent the light connecting them as a linear approximation of the particle trajectory, which is normally represented as a matrix. And then for node update and neighborhood aggregation, a transformation function is applied here to combine aggregated information with our current nodes representation. And in this instance, you might use a graph convolution layer. and the output prediction inference tasks such as like nodes or edge classification. So the point of the project was to predict edges between nodes, so a binary classification of either 0 or 1, depending on whether an edge exists between two nodes or not. And one model that I use was called Silly EC, which is a simplified event data where like the PT is like greater than like 1 GeV truth cut. And it takes edge attributes as inputs and passes through linear layers with ReLU activations. So a rectify a linear unit and activation function to help solve the vanishing gradient issue. And then a sigmoid activation, which outputs the probability of an edge belonging to a certain class. So receiver operating characteristic. A curve assesses the performance of the classification model, and it takes in like a true positive or true negative, where true positive is the probability that an actual positive will test positive or a negative will test negative for true negative. And then false positive or false negative would incorrectly predict a positive or a negative class respectively. So these are the equations that you use to determine true positive and false positive. So it visualizes the trade-off between like is true positive rate and false positive rate across different classification thresholds. And the area under curve quantifies the overall performance of a classifier across all positive thresholds. So this is the ROC curve that I got using the event data that I mentioned, like the Silly EC model. And on the x-axis false positive and y-axis true positive rate. And as you can see, like the model performs like decently well. And the area under curve is like 0.93. Thank you. That's all I could get to. It was a steep learning curve for me, and my term ended before we got to actually use like interaction neural networks.
Okay, thank you, Refilwe. Any questions for Refilwe?
So then, the project's name is developing. The goal was to develop an automatic differentiation pipeline for a thing which is generally known as a stochastic program. In the context of high energy physics, such stochastic program might be like some physical process simulator, which uses some random elements during the course of this of execution of this simulation. So mathematically, it's some map from the input space, random element space, and some initial parameters, and that was the reason why I wanted to annotate. I see, Rob, if you're the host, perhaps you disallow presenters to make annotations on the screen. Could you allow me to do that, or like right-clicking on the user and enable annotation or something like that? Can you hear me now or not? Okay then.
Yeah, I can hear you. Yeah, I can hear you. I'm just not familiar with the
Zoom interface.
Oh, okay. Here I got it.
Okay, then I'll try to simply talk through the presentation. We consider the input parameters x like fixed inputs. For example, these are some priorly known these are some conditions for over which we generally do not want to optimize, and theta as theta we consider like with probabilistic inference, etc., etc. We consider them some inputs of the system, like initial conditions of the experiment, some initial arrangements, or like physical parameters over which we want to optimize and infer. And actually, f could depend on theta, or it could be like some subspace in Rn, etc., etc., and f could depend in various ways on these parameters, like explicitly, if this is partially a deterministic function, maybe some complex with a lot of compositions, functions of this parameter theta, or it can be implicitly dependent on them via probability distribution over the sample space omega. And in practice, it's every physical, every stochastic simulation. It relies on random number generators like Mersenne twistor, which is perhaps the most common. And these random numbers are transformed into the samples from probability distribution via inverting the cumulative density function from this distribution, and thus comes the dependence on theta. And let us go to the examples. One of the most basic examples are simply programs which sample the examples, provide samples of from some distribution. It could be like perhaps the simplest distribution you could imagine is a Bernoulli one. We can like explicitly take theta as its parameter, take more complex dependence. We can generate, as you can see on the right part of the slide, some even more complex functions. And they're getting composed and stacked as one develops more complex. Perhaps let me go right away to some complex example, like that one, which is a toy example of particle shower simplified just in 2D case. And it is an iterative simulation which reuses, which is here defined recursively on one hand side, and on the other hand, it uses some complex custom probabilistic distribution, which depends here on single input parameter theta, but in practice on like quite a lot. And what do we usually want to do with such simulations, etc., etc.? We usually have like some maybe experimental data, the results of the ensemble of such simulations, and we usually want to here f I made an example. That's why I wanted to annotate something, maybe to write formula or two. Here inside an expectation, f could mean not just a result of a simulation, but perhaps a loss function of comparing the results of this stochastic simulation to the actual experimental data. And in many cases, we want to obtain something which will resemble the derivative for an ensemble. And this, in most cases, will be the derivative of the mean. And here I write theta near the expectation symbol to emphasize on the also an implicit dependence of f on these parameters, not only explicit. And here everything depends on the differentiability properties of the function over which we ensemble, and its probabilistic distribution if this function is a random one. And why we ensemble? Because this is a random function. Stochastic program, random process with respect to parameter set theta, as to put it mathematically. And if the differentiability properties are good ones, then we have a pretty straightforward answer, which could be made by a simple derivation, given that we can simply exchange the integration symbol or the summation if the variable is discrete over the sample space and simply take the derivatives. So we here have on the right hand side, inside the expectation symbol, first part of the sum is the pathwise estimator of the derivative, and the second part of the sum is where the derivative is taken of the logarithm of the density, or just the probability distribution, if this is a discrete one, a score function estimator. And their sum gives good, like an unbiased, because we have an expectation of this estimator gives us exactly what we want. Estimator of something like a gradient in this case, but here it has in this article, people describe that it has a great composable properties. One can simply reduce this stochastic case to ensembling over deterministic cases, and in each this deterministic case, automatic differentiation could be done greatly, because it's simply a problem of to differentiate composition of differentiable functions in a deterministic case. But what if here, yes, here actually the results from this paper, like everything which I described in words now, and yes, like we define this surrogate loss function and simply differentiate it deterministically, and then we can like average it over many samples of the computation results of the stochastic program and obtain an unbiased estimator with very quite low variance. And what if the differentiability requirements in this condition 1 simply, if this is not a composition, like very complex composition, if this is like a single random evaluation, like these simple examples I've perhaps shown here, not on the right-hand side, perhaps on the left-hand side already, and I'll tell you why this has complications. If these functions have bad differentiability properties over theta, then we have a problem, because even for the simplest case, like it's Bernoulli variable, it's either 0 or 1, given the probability theta. If we simply use this quite a decent unbiased estimator of the derivative, we will obtain the expectation of Bernoulli variable is the probability of obtaining success itself, so it's theta. Derivating by theta gives 1. On the right-hand side, we have a problem because the pathwise estimator, like this first part of the sum, it's infinite on a set of negligible probability due to the discrete bump, and it is 0 everywhere else. And the derivative of the logarithm is simply undefined here. So score function is undefined in this case. So we have like 0 on the right-hand side and 1 on the left-hand side. So this approach is not usable even for such simple case of discrete random variable, which has not even differentiable. It has even non-continuous dependence on the parameter. And in this case, this is also the issue, because there should be Bernoulli distribution. Here we use, even in this simple case, we use Bernoulli distribution to make decisions in a simulation, whether we go in either one or another branch of the computation process. And what if we use even more complex probability distributions? We then arrive at a problem of defining how to do this, and this is still possible to do. That's what I'm doing in the context of this internship. I am trying to rewrite the stochastic. Actually, as of now, I'm trying to rewrite the like simplifications of the actual simulations utilized in the pipelines in various HEP collaborations here at IRIS. And the ultimate goal is to, even outside the context of the fellowship, is to rewrite the code for the perhaps one of the working horses of this pipeline, the GN4 particle shower simulator. And here is the paper which is like my Bible now, which provides me with a framework with which it is possible to do that. So there is a specific technique of defining the estimate of the derivative to put in the right-hand side, and actually the the methods of defining this mathematical concept in code was explored by me, and as of now yet to be implemented in languages other than Julia. For now, I've been writing this let's put it, stochastic derivation pipeline for the exemplary simulators in Julia. That's perhaps what I wanted to tell you today, and I hope to share further results and the results of ensembling over some large simulation further. Thank you for attention.
Thank you, Oleksii. Sorry for the technical problems. Any questions for Oleksii before we move on to our last talk? All right. Sam, you're up next if you want to go ahead and share your screen.
Hi everyone. For IRIS-HEP Fellowship project, my project was to implement REANA workflow for dark matter searches. And my mentors were Lucas Henrich, Matthew Fickert, Amy Roberts, Jordan Stark, and I'm Sam Dio. I major in computer science, and I go to Fisk University here in Nashville, Tennessee. So talking about the tool that I used, REANA, it is a platform for reproducible data analysis, which facilitates reusable data analysis and reproducible research. It has been extensively used for running containerized workflows of LHC experiments. And this project's aim was to implement a REANA workflow for galaxy rotation curve fitting analysis to improve replicability and to provide a starting point for future research. As you can see, we can connect REANA client with our browser from command line interface, and we can run our containerized technology in the REANA cluster, specifying all the packages and everything. We'll talk about it more, but yeah, my target analysis was galaxy rotation curve fitting model. It's available in GitHub as an open source model, and the contributors were Sophia and her team. And yeah, so breaking the fact, galaxy do not rotate the way we think. As we can see in this first video, galaxy seems to be, things seem to orbit faster in the center, whereas much more slowly when you go far. However, whole galaxy is actually rotating at roughly constant speed. We can see here in the graphs, which is velocity drawn opposed to distance. We see here the velocity is almost constant as we move further from the center. The graph, it can be seen here in the bigger as well. The yellow line represents what was expected, but however, the observed galaxy rotation curve is something else, says something different story, and the velocity seems to be constant. Thus, this kind of gives suggestion that there are some mass outside in the galaxy which do not absorb or reflect or emit light, so they cannot be detected by observing electromagnetic radiation. And yes, that's called dark matter. And the analysis and study of galaxy rotation curve and the model itself is really significant and vital for dark matter search research. Yeah, so my target analysis consisted of 5 kinds of data sets. One was LCM fits, which was randomly collected rotation curve data used primarily from 2011 to 2017 to tune the model. Another was MEGA, Milky Way model from Stacy MEGA, informed from data and MOND. Another was Spark Galaxy. Spark, it was a database of 175 galaxy rotation curves and photometry from MEGA. Some overlap with the galaxies in LCM fits because it has the same rotation curve data, and some are different. Yeah. Another data was SUSOFU. It was Milky Way model from SOFU, and little data things. It was some small dwarf galaxies. So my data was most of the data were in .dat or CSV format. Here you can see I have attached a sample data of I think this is from LCM fits. And this is my model. I had a model in a Jupyter notebook. It loaded all the data, did the analysis, visualized the analysis from the data. And these were the visualization we can see. Here are some really interesting graphs to look at, and probability plots. This is entirely from the analysis of the galaxy rotation curve data that I talked about previously. And these graphs are actually the output of the model. Here you can see the bigger one and what each of the line represents. So my roadmap for this project was, for week 1 to 3, I did a literature review to understand about galaxy rotation curve fitting model and dark matter searches, and to get familiar with the tools that I'll be using. For week 4th to 6th, I studied all the target analysis. My target analysis, I asked several questions with my mentors, and they were really helpful for throughout this process. And then I had to containerize all the important information from the target analysis in specifying the packages and dependencies. Third was to get familiar with the REANA workflow. And for that, I implemented an example analysis. And others were to optimize and in present. Yeah, my last day of the fellowship is October 31st. And what I did was I leveraged the Conda environment using an environment.yml file to specify the required packages and dependencies of the target analysis. I played around with REANA using a sample analysis to understand its functionalities and capabilities. And I must say it's a great tool. I created then REANA.yml file with the workflow specification for the dark matter searches. Here you can see the REANA.yml file, which specifies the version of the REANA that I'm using. It was recently updated, I think. Then my inputs are files. I have Python files, CSV files, data files. My model.ipynb is using functions from Python files. It's loading CSV files and data files as inputs. And yeah, the important part is the workflow. Here I have specified my environment and imported all the data. And you can see in the second picture that I have outputs, and the most important thing is the command. I have used nbconvert to execute my model of model.ipynb, and these outputs are stored in the PNG files. Unfortunately, I have not been able to run the analysis successfully. I did run the example analysis successfully, but I'm still trying to debug it. It failed after 11 hours, 10 hours. So my mentors are trying to help me, and yeah, hopefully I'll get it done by October 31st, and I'm excited to share what I'll be able to achieve. My sincerest gratitude to whole IRIS-HEP team, Robert, my mentors, and everyone. Thank you so much. If you have any questions, feel free to ask me.
Nice talk, Sam. Any questions for Sam? All right. Thank you all for your presentations today. Thank you to all the mentors. Thank you for all our visitors who came to watch their talks.